Hello. Hello, good morning. I'm discussing about stereochemistry, the branch of chemistry which deals with the structure of compounds in three-dimensional space is called stereochemistry. This topic is under B Sc First year, Trivandrum University, IST, Institute of Science and Technology, B Sc First year. Okay. Stereochemistry, the branch of chemistry which deals with the structure of compounds in the three-dimensional space is called stereochemistry. Structural isomers and stereoisomers. Structural isomers due to different in arrangement of atoms or groups within a molecule is known as structural isomers. And butane, isobutane. Stereoisomers, the particular types of isomers that are different from each others only in the way the atoms are oriented in space are called stereoisomers and phenomenon known as stereoisomerism. Geometrical isomers, it is stereoisomers due to different orientation of groups or functional groups is called geometrical isomers. Cis-butanediol malic acid, trans-butanediol acid, fumaric acid. Optical isomers and optical active compounds exist in two isomeric forms that rotate the plane polarized light in opposite directions. They are called optical isomers, and the phenomenon is called optical isomerism. Figure optical isomers of lactic acids, levulactic acid and dextrolactic acids. Structural isomers, skeletal or chain isomerism. Structural isomers due to different chain or skeletal of carbon atoms. Structure of all isomers of pentane, n-pentane, isopentane, neopentane. Positional isomers, structural isomers which have same functional group but different position is known as positional isomers. 1-pentanol, 2-pentanol, this is the position. Functional isomers, structural isomers due to different functional groups. Hal alcohol, dimethyl ether. Metamerism, structural isomers due to different alkyl groups attached with same functional groups are known as metamers, and the phenomenon is known as metamerism. Example, diethyl ether and methyl propyl ether, diethyl, methyl propyl ether. Tautomerism, functional isomers which exist in dynamic equilibrium with each other. For example, enol form, this is the keto form. Optical activity, the substance which rotate the plane polarized light towards clockwise or dextrorotatory or anticlockwise or laborotatory is called optically active substance, and phenomenon is called optical activity. The substance which do not rotate the plane polarized light are called optically inactive. Polarimeter, the instrument used for measuring optical reaction or specific rotation, is called polarimeter. Polarimeter consists of a light source, two nickel prism, and a tube to hold the solution of organic substance. Figure a schematic representation of polarimeter. Light source, ordinary light, nickel prism, polarized light, sample solution, rotated polarized light. Specifically, rotation of optically active substance, it is defined as the optical rotation produced by a compound when plane polarized light passes through the 1 decimeter length of the solution at concentration 1 gram per liter. The angle of rotation of plane polarized light or optical rotation of an organic compound depends on kinds of molecules that light encounters in its path, which is turn depends on concentration of solution, use and length of polarimeter tube, temperature wavelength of light, and nature of solvent. Alpha equal to T lambda, alpha T lambda, okay, alpha L into D, alpha observed rotation in the degrees, the concentration of substance or density of pure liquid in gram per liter, the temperature. Plane polarized light, property of certain types of electromagnetic radiation in which direction and magnitude of the vibrating electric field are related in the specified way. Plane polarized light, property of certain types of electromagnetic radiation in which direction and magnitude of the vibrating electric are related in a specified way. The electric vector representing the magnitude and direction of the electric field in a wave light is perpendicular to the direction in which the wave is moving. Schematic representation of plane polarized light and ordinary light. Polarized light, ordinary light. Randomly oriented light, polarized filter, plane polarized light. So polarized light which consists only of waves that vibrate in one direction, but unpolarized light consists of waves moving in the same direction with their electric vectors in random orientation. Chiral center, a chiral center is defined as an atom in a molecule that is bonded to 4 different chemical species. Example, the central carbon is serine is a chiral atom, amino, hydrogen, carboxylic, and alkyl groups. Example of amino acid in the molecules are mirror image of each other, enantiomer, serine, chloroiodomethane sulfonic acid, not superimposable enantiomers, chloroiodomethane, chloroiodosulfonic acid, chloroiodomethane sulfonic acid. This is the isopropyl chloride superimposable, no enantiomer. It means the mirror image of this compound is exactly fit on this carbon. It's also not chiral center. Serine, tertiary halides. Chirality is a geometric characteristic that the structure of an object cannot superimpose with its mirror image. Each chiral object may have 2 different chiral structures called enantiomers. Each chiral object may have 2 different chiral structures. Each chiral object may have 2 different chiral structures, enantiomers or enantiomers, and the enantiomers are usually labeled as left-handed or right-handed form. An object is said to be chiral if the object and its mirror image are non-superimposable, just like our right and left hand. Now you must be wondering what we mean by non-superimposable. When the mirror image of the object is placed over the original object and they do not overlap as shown in the figure below, then the object and its image are said to be non-superimposable. Chiral, this is the chiral, left hand, right hand cannot be superimposed. Left-handed, right-handed. Superimposable mirror image compound, a chiral that is non-enantiomers. A superimposable mirror image means that the one molecule could be placed on the top it's the mirror image and with perfect fit. Superimposable mirror image. A superimposable mirror image means that one molecule would be placed on the top its mirror image and would perfect fit. It means the relative position of the atoms in the molecules can be twisted without breaking bonds to make these molecules the exact same. For example, isopropyl chloride mirror image. Isopropyl chloride mirror image. This is superimposable, no enantiomers. Non-superimposable mirror image, chiral, that is enantiomer. Or non-superimposable mirror image enantiomers means that no movement about the axis can make these molecules exactly identical. They are exact opposite of your left and right hand, not superimposable enantiomers, chiral molecules. Example, chloroidomethane sulfonic acid. Mesocompounds. In the simplest case, a compound with two similar chiral carbon atoms, two chiral centers where there is the same set of four groups at each chiral center, the combination where the four groups are arranged such that the centers are mirror image of each other. That is, where the molecules are as an internal mirror image, that is mirror plane, is a mesocompound. See, in the mesotartaric acid, the molecules between the mirror, that is the internal mirror image, is ordered. Mesocompounds are optically inactive due to internal compensation. The optical rotation due to one half of the compound is equal and opposite to the rotation due to another half and cancel each other. Enantiomers, non-superimposable, that is chiral. Stereoisomers, which are the non-superimposable mirror image of each other, are called enantiomers. This we have already discussed. Isomers that are mirror image of each other called also enantiomers. We can define in this way. Isomers that are mirror image of each other are called enantiomers. Properties of enantiomers. Enantiomers have same physical properties but differ in direction of rotation of plane polarized light. They have same chemical properties except optically active reagent. The equal amount of enantiomers is known racemic mixture. Enantiomers cannot be separated by fractional distillation physical technique. Diastereomers are compounds with two dissimilar chiral carbon atom. It is stereoisomers that are enantiomers that is not mirror image of one another and non-superimposable of one another. Such type of pairs of stereoisomers which are not mirror image of each other are called diastereomers. It is stereoisomers that are enantiomers that is not mirror image of one another and non-superimposable of one another. Such type of pairs of stereoisomers which are not mirror image of each other are called diastereomers. For example, 2-chloropropane 2-ol. 2-chloropropane 2-ol. 2-chloropropane 2-ol. Structure first and second are mirror image and not superimposable chiral. So first and second are enantiomers. But structure third is neither superimposable on first nor the mirror image of first, that is second. So pair of third in first also and third in second are stereoisomers but not enantiomers. In this way, third is diastereomer of first and second. Similarly, fourth is the diastereomers of first and second. Properties of diastereomers. Diastereomers have also similar chemical properties. Rate of reaction of diastereomers with a given reagent are generally different. Example of diastereomers: 2-chloropropane 2-ol. 2-chloropropane 2-ol. Sorry. Example of diastereomers: 3-chloropropane 2-ol. Structure first, structure second, structure third, and structure IV. Properties of diastereomers. Diastereomers have also similar chemical properties. Rate of reactions of diastereomers with a given reagent are generally different. Diastereomers have different physical properties like melting point and boiling point. Diastereomers can be separated by fractional distillation and chromatography. Racemic modification or racemic mixtures. When equal amounts of two enantiomers are mixed together, it gives an optically inactive form called the racemic modification mixtures. It is denoted by using the prefix plus minus or RS or DL before the name of the compounds. Example: equal amounts of plus lactic acid and minus lactic acid. Resolution of racemic modification. The separation of racemic modification or mixture into enantiomers is called resolution. Mechanical separation or crystallization method. It is adopted by Pasteur for separating enantiomers when the racemic modification is crystallized from solution. We get two types of crystal which are mirror image of each other, consisting of plus and minus forms, which can be separated by picking with the help of tweezers and powerful lens. Example: ammonium tartrate. Biochemical methods. Certain microorganisms grow in a racemic mixtures. This newly grown microorganism consumes one of the enantiomers while leaving another unaffected. Example: penicillium glaucum. When placed in plus minus tartaric acid, it contains only plus tartaric acid but unaffected minus tartaric acid. Chemical separation. In this method, the racemic modification is treated with an optically active reagent to get a pair of diastereomers. This diastereomers is separated by the physical methods such as the fractional distillation, crystallization, etc. Let a racemic modification of mixtures versus plus minus acid, which is the treated with minus base, which gives the mixture of salts. This is the racemic mixture treated with minus base, salt plus salt of minus acid, minus base, salt of plus acid, minus base, diastereomers of separable. If we edit H plus minus acid, enantiomer pure form. If we edit H plus plus acid, enantiomers pure form. Racemization, the transformation of an optically active enantiomer to the optically inactive racemic modification under the influence of heat, light, or chemical reagent is known as racemization. For example, plus or minus lactic acid on warming, which was sodium hydroxide converted into lactic acid, plus or minus lactic acid plus NaOH warm plus minus lactic acid. Configuration, the spatial arrangement of atoms or groups of atoms around a particular chiral carbon is known as configuration. The arrangement of atoms in a space of a molecule of defined constitution without regard to rearrangement that differ only as the after rotation, one or more single bonds defined as configuration. Or the spatial arrangement of atoms or group of atoms around a particular chiral carbon known as configuration. So this definition clears that cis and trans isomers. Absolute configuration, relative configuration, absolute configuration of diglyceride, L-glyceride. Relative configuration, it refers to correlative configuration, that is, relative configuration which relate configuration of one compound with other. Suppose a child has not learned to distinguish right from left and left from right, given so. The child cannot tell which is right and which is the left. That is the absolute configuration of so, but the child may be able to tell that are the different in that of they are fits one of her is fit A, but not other fit B, and vice versa of the other shoe. In this way, child can determine the relative configuration of shoe. Cis relative configuration are absolute configuration. Absolute configuration and relative configuration. Absolute configuration is stereochemistry, is the arrangement of atoms or groups of atoms that is described independent of an ordered atom or group of atoms in the molecule. Relative configuration in the stereochemistry is the arrangement of atoms or groups of atoms that is described relative to other atoms or groups of atoms in the molecule. Atomic arrangement, independent of the position of the order substituent, depends on the position of the order substituents. Designation can use the sign of the rotation and the designation R or S. Cis, trans, E, and Z. Intrazine and Jusamin designation are used. Sequence rule, the determination of absolute configuration is not so easy, and first method to determine absolute configuration was developed by Bisvoet and Kine-Hole-Prelog rules is known as a sequence rule. Sequence rule to assign the priorities to substituents. Rule 1, substituent that has the higher atomic number take a priority over lower atomic number. See, in this example, chlorine, sulfur, hydrogen, and iodine. So chlorine is the highest, iodine, chlorine, sulfur, hydrogen. So iodine has the highest atomic number, so first priority, and the second atomic number chlorine, second priority. Third atomic number is sulfur, and least atomic number 1, hydrogen, so least priority. Rule 2, if the rule 1 fails to decide the relative priority of two groups, it is determined by the similar comparison of next atom to in the group and so on. In another words, if two atoms directly attached to chiral center are same, the next atoms attached to each of these atoms are compared. For example, two of the atoms directly attached to the chiral center are carbon themselves. To decide priority between the two groups CH3 and CH2CH3, methyl carbon is linked to the three hydrogens, that is the sum of the atomic numbers is 3. The methyl carbon of the ethyl group is linked to the two hydrogens and one carbon directly, that is sum of the atomic number 8. Thus, ethyl group gets its priority over the methyl. See, in the 2-butanol, here the highest atomic number is the oxygen, so number 1, and that is the another is carbon is joined to carbon in this methyl group, and this ethyl group also carbon, and least is the hydrogen, no doubt it is definitely 4, but these two carbon which have the second and third priority is the question. In this case, you should add the second number and similar to sequence rule 1. In case of methyl, atomic number of carbon is 6 and 3 hydrogen, that is the 8. But in case of this ethylene uh, carbon is joined to 2 hydrogens and also another carbons. So this have 6, 6, 12, 12 to 14. That's why the next second priority is the ethyl and the third priority is the methyl. This is another example. Also another example. Rule 3, if one of the atoms connected to the competing chains has the double or triple bond, the chains has higher priority with double or triple bonds. In this case, the first priority is the oxygen due to highest atomic number, but second and third that is the CSO aldehyde group, and this is the alcoholic group. So in aldehyde, that is the double bond with carbon. So second priority over this alcoholic group to the carbon. So second and third and fourth number. Specifications of group configuration R or S. Can Ingol and Perloff develop a method to design it, the configuration of all the molecules containing the asymmetric carbon atom chiral center, which is known as the Can Ingol, Perloff or RNS system. Step 1, in this step, different atoms or groups of atoms attached to the chiral carbon atom are assigned a sequence of priority order by sequence rule. Step 2, after deciding the priority order of 4 atoms or groups of attached to the chiral atoms, then the molecules is visualized in such a way that the atom or group of atom of lowest priority is directed away as the while the remaining 3 groups are priority towards us. Vectors are sinister, and these 3 groups in the order of their decreasing priority is clockwise direction. The configuration is specified as vectors are, on the other hand, decreasing priority in anticlockwise direction. The configuration is specified as sinister as R glyceride and S glyceride. Configuration of on the basis of projection formula. When a compound is represented by a Fisher projection formula, the configuration can be easily determined with constructing model. To determine whether I travels clockwise or anticlockwise, we have to place the group or atom of the lowest priority at the bottom of Fisher projection formula. The atom or group of lowest priority is at the bottom. In such case, simply rotate the I in the order of the decreasing priorities. The configuration is R if the I travels in the clockwise direction and S if the I travels in the anticlockwise direction. Example, R glyceride. The atom group or lowest priority is at the top. In such case, rotate the molecules by 180 degrees so as to bring atom group of lowest priority at the bottom. This can be done by the reversing the position and all the atoms or groups, then find the direction in the order of decreasing priorities. Example, S-bromide-methane. The atom group of lowest priority is at the right hand side of the horizontal line. In such case, change the position of the atom or groups in the clockwise direction, so that atom group of the lowest priority comes at the bottom, but not change the position of the atom group at the top of the vertical line. Then find the direction in the order of decreasing priorities. Example, S-bromochloroiodomethane. The group or atom of lowest priority at the left-hand side horizontal line. In such case, without changing the atom or group vertical, change and other groups anticlockwise, so that atom of group lowest priority comes bottom and find direction in the priorities R-bromomethane. See, in this example, the lowest priority is left hand side. So the left hand side of lowest priority is rotated in the uh, clockwise direction, and this hydrogen and this, but the top is on chain. So this is the clockwise direction. So it rotate anti-clockwise direction. Uh, this uh, this hydrogen comes in the bottom. So chlorine left and iodine here. So 1, 2, 3. This is the clockwise. In this case, the lowest priority is the right hand side, and this rotates. In this case, the you number the carbon, and in this case, the lowest priority on the right hand side. So you rotate to clockwise direction, and it comes at the bottom. So, and you have to similar as before as this example. In this case, also the lowest priority is the right hand side, left hand side. You rotate this. In this case, the lowest priority, this carbon, so this is rotate in left hand side. Okay, in this case, the C2S5, COS, says the lowest priority is the on the left hand side. The numbering of two carbon. So first you number 1 to 3, and you have to write like this and flow as before rules. In this case, the lowest priority is left hand side. So rotate in the anti-clockwise. These are the homework. You can solve these examples. Generation of chiral centers, only one chiral center. One of the products of chlorine compound on the and butane is the chiral compound, that is sec-butyl chlorine. It can exist in enantiable first and second, which is by RNS respectively. Asymmetric synthesis, the preparation of an optically active disymmetric chiral compound from non-disymmetric molecules under the influence of an optically active substance, is known as asymmetric synthesis. The preparation of optically active asymmetric compound from non-disymmetric molecules under the influence of an optically active substance. For example, pyruvic acid is direct reduction yields optically inactive so racemic lactic acid, but pyruvic acid are pure pre-stratified with optically active, say alcohol, menthol, and reduction and the subsequent hydrolysis predominantly minus lactic acid. If an atom or group of atoms directly attached to chiral carbon, atom is replaced by another atom or group of atoms, the configuration of products is found to be different from that of starting compound. Such phenomenon which involves inversion of the configuration during reaction is called Walden inversion. The atom or group of lowest priority is at the bottom. In this case, you rotate the compound. Uh, if lowest priority is the bottom, you rotate the I in the number. In this case, 1, 2, 3. This is the clockwise, so R glycerolized. The group of atom lowest priority is the top. In such case, the rotate the molecule by 180 degree so as to the bring atom group of lowest priority at the bottom. This can be done by reversing the position and all the atoms or groups, then find the direction in the order of the decreasing priority as bromoiodomethane. See, in this example, the lowest priority is in the top. So you rotate 180, top, bottom, left, right, right, left. The atom or group of lowest priority is at the right-hand side of the horizontal line. In such case, change the position of the atom or groups is clockwise direction. So that atom or group of lowest priority comes at the bottom but not change the position of the atom or group at the top of the vertical in. Then find the direction in the order of decreasing priority. Example S bromochloride methane. In this example, the lowest priority is the right hand side. We rotate the clockwise direction, that is it comes in the bottom. See, in this example, the hydrogen is the right hand side. If you rotate it clockwise direction, is the bottom, and the chlorine is in this, and this is also seen in. So you have to rotate the I 1, 2, 3, 4. It is the S anti-clockwise. In such case, without changing the position atom group at the top of the particles in, change the position of the other atoms groups in the anticlockwise. So that atom group of lowest priority comes at the bottom, then find the direction in order decreasing priority are bromochloride Lowest priority is left hand side. Rotate the bottom, and chlorine right inside. This iron is the left inside. Okay, thanks for watching. It's all about the stereochemistry in regards to BSc first year, Tririvan University, Institute of Science and Technology. Okay, thanks for watching. It's now your exam is coming near about, and best of luck, all of you. Thanks for watching, and request you all like, comment, share, and subscribe. Bye bye. See you again.